Hello, and welcome to my talk on the approximation ratio of the k-opt and Kernighan algorithm for metric and graph TSP. My name is Xianghui Zhong, and I'm from the University of Bonn. Let's start with the definition. An instance of the metric traveling salesman problem, short metric TSP, is given by n vertices and their pairwise distances. The distances satisfy the triangle inequality. The task is to find the shortest cycle visiting every vertex exactly once. This problem is NP hard, so no polynomial algorithm is expected. Therefore, several approximation algorithms are considered. An approximation algorithm computes a solution that has at most r times the cost of an optimal solution in polynomial time. R is called the approximation ratio of the algorithm. The currently best approximation algorithm in respect of approximation ratio is that of Kosofidis, which was independently developed by Serdyukov, with an approximation ratio of 3/2. But in practice, other algorithms with a worse theoretic guarantee usually perform better and have better runtime. For example, the k-opt and Kernighan algorithm fall in this category. Our paper will focus on these two algorithms. So let's briefly summarize the main steps of the k-opt algorithm. It is a local search algorithm, and k is a natural number which is fixed in advance. So it starts with an arbitrary tour, and in every iteration it tries to replace at most k edges by other edges to make the tour shorter. If this is not possible anymore, it outputs the tour. Such a tour, which cannot be improved by replacing at most k edges by other edges, is also called k-optimal. So in the left figure, you can see an example of a tour consisting of the green edges and the red edges. And the algorithm can now replace the two green edges by the blue edges to get the new tour shown in the right figure, which is shorter than the previous one. The Kernighan algorithm is also a local search algorithm, so it also starts with an arbitrary tour and tries to improve the tour in every iteration. But in contrast to the k-opt algorithm, and the maximum number of edges it replaces in every iteration, so k in this case, is not fixed in advance. So it is a little bit more complicated, and this talk will just focus on the k-opt algorithm. So what is known about the k-opt algorithm? For the approximation ratio of the 2-opt algorithm, in the metric case, Plesnik, Chandra, Karlov, and Tovey showed that the approximation ratio is between square root of n over 8 and 4 times square root of n. Levy and Juve improved the upper bound to square root of 8n, and recently the approximation ratio was shown to be exactly square root of n over 2. For the k-opt algorithm, only a lower bound of a quarter times 2k root of n is known, and no other non-trivial upper bounds. Of course, you can take the upper bound of the 2-opt algorithm and apply it for the k-opt algorithm, since the k-opt algorithm also produces 2 optimal tours. The same situation also holds for the Kernighan algorithm. There we have no lower bound and also no trivial upper bound, only the one you obtain from the 2-opt algorithm. For the 2-opt algorithm on graph TSP, so graph TSP is a special case of the metric TSP where the distances arise from the graph metric. Only a lower bound of 2 times 1 minus 1 over n is known, and also there are no non-trivial upper bound. the new results of our paper, we show that assuming the Erdős conjecture, I will explain later what it says, the approximation ratio of the K-op algorithm is asymptotically case root of n. Unconditionally, that means without the Erdős conjecture, we give bounds on the approximation ratio that are tied up to a factor of O log n. So we have to say that these bounds depend on some functions from the extremal graph theory. The upper bounds also applied for a parameterized version of the Kernighan algorithm with appropriate parameters. For the graph TSP, the approximation of the K-op algorithm is asymptotically bounded above log n over log log n and below log n over log log n to the 3.17. With these results, we solved 2 of the 4 open problems from the Chandra paper, from which many lower and upper bounds previously known are origin drawn. Namely, can the upper bound of the 2-op algorithm given in the paper be generalized to the K-op algorithm so that for increasing K, the performance guarantee improves? And the second question is, can we show better upper bounds for the Kernighan algorithm than the upper bound obtained for the 2-op algorithm? So in our case, our analysis yields an upper bound of cube root of n for the original version of the Kernighan algorithm, while the trivial upper bound we obtain for the 2-op algorithm is square root of n. Okay, before we dive into the analysis, I want to state the Erdős conjecture first. For that, we need to state a problem from the extremal graph theory. So given a graph with n vertices and girths at least 2k, the girth of the graph is just the length of the shortest cycle. So that means that the length of the shortest cycle is at least 2k. What is the maximum number of edges in this graph? So intuitively, you have a graph with fixed number of vertices, n, and no short cycles. So the question is, how many edges can this graph contain? So if it contains too many edges, then it has to contain a short cycle. This number is asymptotically bounded above n to the 1 plus 2 over 3k minus 5 and below n to the 1 plus 1 over k minus 1. And the Erdős conjecture precisely says that the upper bound is tied, so that this number is asymptotically n to the 1 plus 1 over k minus 1. This conjecture is proven for k equals 2, 3, 4, and 6, and therefore, in these cases, our analysis yields a tight asymptotic bound of k's root of n. So let us briefly summarize the main ideas for the upper bound on the approximation ratio of the K-op algorithm for matrix TSP. For all other lower bounds on the Kernighan algorithm and for graph TSP, we refer to the full version of the paper. So let's start with the general strategy for the upper bound. Assume that an instance with k optimal tour t is given, and let us, without loss of generality, assume that the length of the optimal tour is 1. We can achieve this just by scaling. Note that if the K-op algorithm would start with t, then it would immediately terminate, since t is already k-optimal and no improvements are possible. Therefore, if we can get an upper bound on the length of t, this would imply an upper bound on the approximation ratio, since we have assumed that the length of the optimal tour is 1, and we did not make any further assumptions of t except the k-optimality. So for such an upper bound, we want to show an upper bound on the number of long edges in T. And long just means high cost. And so, for example, you can imagine that every edge with cost greater than half is long and every other edge is short. So how to bound the number of long edges in T? First, we construct an auxiliary multigraph G1 from T that contains all long edges in T. Then, we construct an auxiliary multigraph G2 from G1 that contains a quarter of the long edges in T. We show if G2 contains a short cycle, then T is not K-optimal. Therefore, G2 does not contain a short cycle, and this implies the lower bound on the girth of G2. And this yields an upper bound on the number of edges in G2 by the results from the extremal graph theory, for example by the Erdős-Girth conjecture. And so we obtain an upper bound on the number of long edges in T, since G2 contains at least a quarter of the long edges in T. This gives us an upper bound on the length of T, since we have bounded a number of long edges, and in the end we get an upper bound on the approximation ratio, since the length of the optimal tour is 1. So we will focus now on the first 3 steps of this analysis, and the remaining steps are not so hard to show. So let's start with the first one. We construct a multigraph G1. So we want an upper bound on the number of long edges in T depending on the number of vertices in T. Now there's a problem. T contains too many vertices, so if we would perform the whole analysis on T, we would get a bad bound because the upper bound on the number of long edges is depending on the number of vertices in T. How to solve this problem? We construct a multigraph G1 from T by contracting vertices which are near each other in the optimal tour. So you can see in the left figure we have the tour T. Note that T is not an undirected cycle visiting every vertex exactly once, but a directed cycle because we have fixed an orientation. So we just fix one of the 2 possible orientations and consider a directed cycle with directed edges. And in the right figure we have the multigraph G1. You can see that we have contracted some of the vertices, and note that we constructed the vertices which are near each other in the optimal tour, and the optimal tour is not depicted in the figures, so it is not possible to tell from the figures why we contracted these vertices. This can be done such that G1 contains all long edges in T after deleting the self-loops. Because we only contracted vertices which have short distances to each other. So after the contraction and removing all the self-loops, we obtain a multigraph G1 with all long edges in T. So now we have a new multigraph containing all long edges in T, but with fewer vertices. So therefore, if we perform the analysis on G1, we would get a better bound on the number of long edges. We need an additional property for the analysis. Therefore, we'll construct a multigraph G2. So the additional property is in every undirected cycle, every vertex is head of both or tail of both incident edges according to the orientation of T. In this figure, you can see an example of an undirected cycle in G2, and basically every cycle has to have this form. So the next step is to construct the multigraph G2 from G1, satisfying this property and containing a quarter of the long edges. We do this by coloring the vertices of G1 red and blue, and only consider long edges from a red vertex to a blue vertex according to the orientation of T. So we will specify later how we color the vertices. And we delete all other edges to obtain G2. So in the left figure, we have again the graph G1. So in the right figure, we have G2. And you can see we colored every vertex red or blue. And we only consider the long edges from the red vertex to a blue vertex. For example, the top left edge is missing because it is not long. The coloring can be done in such a way that at least a quarter of the long edges remain in G2, because we can just randomly color the vertices and the property is satisfied for the expected value. Okay, now we have constructed the graph G2 and we want to bound the girth of G2. So assume that there's an undirected cycle with two H edges. So in the left figure, you can see an undirected cycle. And the edges of the cycle are colored blue. We will call the edges blue edges. And our aim is now to get them bound on 2H so that we can conclude that there are no short cycles in G2. Note that we can assume here that the number of edges is even in this cycle, because you can see easily from the construction that the graph is bipartite. By considering the preimage of the cycle, we get an alternating cycle for T. So if we consider the preimage of the blue edges in G2 in the left figure, we get the blue edges in the right figure, so the blue edges in T. And we can now add the green edges, connecting the blue edges to an alternating cycle for T. So what is an alternating cycle? An alternating cycle is just a cycle consisting of edges in T and edges not necessarily in T. And in our case, precisely, the blue edges are in T and the green edges are not necessarily in T, and they alternate. So we see that the green edges are cheap since we contracted vertices which are near each other. That means that every green edge connects two vertices which are contracted to a single vertex in G1. So since we only contracted vertices which are near each other or have short distance to each other to a single vertex in G1, we can conclude that the green edges are cheap. Now we can augment that alternating cycle. That means that we remove the blue edges and add the green edges to get a union of cycles. We get a union of cycles because the degree at every vertex is still 2, since we either did not change the degree or added a green edge and removed a blue edge. So after the augmenting step, we get the union of cycles shown in the left figure. And now the tour can split into at most 2H connected components because we removed 2H blue edges. Now the property of cycles that every vertex is head of both or tail of both incident edges ensures that T splits in at most H connected components instead of 2H. This property is not trivial to see, so you have to believe me here. So now why does it help that we have H connected components instead of 2H? Because now we can add 2 copies of at most H-1 deleted blue edge to reconnect the 2 again and to make the degree at every vertex even. So make the graph Eulerian. You can see this in the figure in the middle. We have added a blue edge that was deleted to reconnect the tour again and add another copy of it, which is pink in this figure, to make the graph Eulerian. Now we can shortcut in a particular way to get a tour T prime. So in the Eulerian graph, we have vertices with degree 4, but in the tour we only want vertices with degree 2, so we can shortcut in a particular way to get the tour shown in the right figure. The tour is called T prime, and we want to show two properties of T prime. The first one is T prime is cheaper than T, and the second one is T prime arises from T by replacing not too many edges. So let's start with the first property. For that, we assume now for simplicity that every blue edge has the same cost. Then T contains 2H blue edges, and T prime contains at most 2 times H-1 blue edges, since we added at most 2 H-1 deleted blue edges and 2 copies of them. Therefore, T has at least 2 more blue edges than T prime, but instead T prime contains the green edges, but we have seen on the last slide that the green edges are cheap. Therefore, T prime is cheaper than T because T contains the 2 extra blue edges and they dominate the cost. So for the second property, note that T prime arises from T by replacing at most 2H edges, since we removed the 2H blue edges. Now we can conclude that 2H is greater than K, since otherwise T is not K optimal, since we have found a replacement of 2H edges to get a cheaper tour T prime. And this is equivalent to 2H is greater or equal to K plus 1, and therefore G2 has girth at least K plus 1, since we have assumed that G2 has a cycle with length 2H. Now we have already a lower bound on the girth of G2. Next, we want to improve this result and show a better lower bound on the girth of G2. So to improve the girth of G2, we want to construct a tour that arises from T by replacing less edges. This can be done by increasing the number of blue edges in T prime. So in the left figure, you can see T. In the right figure, you can see T prime. In order to obtain T prime from T, we removed the blue edges and added the green edges and some of the blue edges and the pink edges. And now note, if T prime already contains many blue edges, then we do not have to remove them and add them later again, so that we can replace less blue edges to obtain T prime. So we want to increase the number of blue edges in T prime. How to do this? We start with the tour T prime, and in every iteration we replace 2 edges to increase the number of blue edges in T prime. So we have an example in the figure. The tour T prime consists of the red edges and the green edges, and we can now delete the green edges F1 and F2 and add the edges E1 and E2 such that the tour contains an additional blue edge, and in this case E1. We have to show that after the replacement the tour is still connected, and we can find enough such replacements such that in the end T prime is still cheaper than T and arises from T by replacing H-1 edges. Now we can conclude that H-1 must be greater than K, otherwise T is not K optimal, and this is equivalent to 2H is greater or equal to 2K, and therefore we can conclude that G2 has girth at least 2k. Okay, now we have a good lower bound on the girth of G2, so we are done with the main steps of the analysis. Let us just summarize the steps of the analysis again. First, we construct an auxiliary multigraph G1 from T that contains all long edges in T. Then we constructed an auxiliary multigraph G2 from G1 that contains a quarter of the long edges in T. We showed that if G2 contains a short cycle, T is not k-optimal, and therefore we get a lower bound on the girth of G2, and this implies an upper bound on the number of edges in G2 by the Erdős girth conjecture, for example. And this yields an upper bound on the number of long edges in T, since G2 contains at least quarter of the long edges in T. And so we get an upper bound on the length of T, since we have bounded the number of long edges in T. And this gives us, in the end, an upper bound on the approximation ratio, since we have assumed that the optimal tour has length 1. Okay, so these were the main steps of the analysis. Thank you very much for the attention.